So we're going to cover chapters 33 through 35 today. So last time we looked at the slopes in multiple regression, but we didn't really look at them graphically, what they mean. So the first thing, an important point in multiple regression is that the slopes control for the other variables. That means they give you the slope holding the other variables in the model, the other x predictor variables, constant. So we talked about this last time. We said that these slopes in the multiple regression are different than in the simple regressions. For example, we're going to continue with the same example. We're looking at, here's our multiple regression equation here. Right here, it's saying that finals equals this partial slope right here, times homework, plus this partial slope times exams. In the multiple regression, these are partial slopes. Both of these are partial slopes. What does that mean? It means that the slopes right here, I say it right here, the slopes in multiple regression are called partial slopes because they quantify the effect of each variable after the other one is controlled for, partialed out, okay? And that's why they are different. Like here's the simple, right here. Here's the this is a multiple regression equation. Why? Because it has two predictor variables, two x's predicting one y. We have homework and exams, both x's predicting the final. So this is the multiple regression, as opposed to the two simple regressions, which would be, here's one of the simple regressions, simple regression equation, which is just, this one is just homework alone predicting y. Okay? So this one right here is bigger than that one, right? It went down in this partial because it's saying what? That for people who have the same exam score, like this group of people, these all have a slope. Look at all these right here. All have the same slope of this small slope of 0.164. All of these. Because they're controlling for exam scores. They're saying if you compare people who have the same exam scores, like these people all have 70s on their exam. So if you compare two people who have a 70 on their exam, the one who has one more homework point, on the average goes up by 0.164 on the final. Okay, whereas this one says we're looking at, this is a different, we'll get to this one next, but first let's just look at these. So how do we actually get this equation for the different exam scores? Like for those who had a 70 on the exam, what are we going to do here? Well, we just use this equation and put 70 in for exams. So they all have the same slope, but they're going to have different intercepts here. So this is plus, I'll just put 0.5824 times 70, and then plus 11.91. And then when I did that, I got 52.678. Okay, so that's this equation. Now, how's this one going to compare? Well, you can see they're parallel, so they all have the same slopes, but this one's going to go up by what? This one has this is somebody who has 70. We'll multiply 70 times this. And the next one will have 80 times that. So it's 10 more. So it's going to go up by about 6. 10 times 0.58. I can write that down if you want. I can say plus 0. You're plus 0. What? 5824 this time times 80. Plus this 11.91. So you can see the difference is it's going to go up by 10 70 versus 80, 10 times that, so about 6. That's an 8 there, right? So it goes up to 58.502. From 52 to about 58. Okay, and the next one's going to go up by about another 6 points, because this one's 90, so we're just going to plug a 90 in there. So here I got 64.326. So you can see what's happening here. All right? That's what we did right here. Now, so what we're doing is we're saying the homework slope in this multiple regression is the effective homework on finals for those who have the same exam scores. Each one of these has the same exam scores. Okay? So for those with the same exam score, the predicted final score is 0.1641 points higher for each 1 point increase in the homework averages. So now, what does this simple regression do here? This ignores. This is the simple one right here. What does this do? It ignores exam scores. But the problem, so you can't tell how much of this right here, how much of this, we'll color it, is due to the homework and how much is due to the part of the homework that's correlated with exams. Why? Because if you look here, the people, this is a simple regression right here. So it has a bigger slope than this one. I've drawn in the stratified ones right here after controlling for exams. So the idea is, look, people have higher homework scores. These are the people with the high homework scores. They also have high exams. They have higher exam scores. And the ones who have the low homework have lower exam scores. So it's mixing up those two things. The simple regression mixes that up. And so it's a bigger slope. So this right here has a bigger slope than this one because it's mixing in exam scores. Exams aren't controlled for. Bigger slope because the effect of exams is mixed in with the homework, so that's why it's bigger. Then when we partial them out, we get an effect when we include exams. It has the effect of breaking the population into subgroups so that we get more balanced groups. So if we're looking at a causal effect, like how much, if you look at this, you think, oh, homework affects finals quite a bit. But that's because if you're thinking of it, does homework cause that much of a difference in finals? No, part of that effect is due to exams. So when you include exams in, then you see, after we already have exams predicting finals, how much more does homework help? And it goes down because they're all positively correlated here. Does that make sense? If they weren't correlated, it would be the same. All right, so that's the idea. And let's move on. Okay. So why don't we look at why don't we put this into 3D now? Because we're squashing this down into, this isn't really the real graph. We have 3 variables here. We have, so we're in a 3D, and we tried to present it in 2D here. So let's draw these 3 the way they look, really, in the scatter plot here. Okay? So let's just draw those in first, what we did. And so can you see we have homework here on this axis. We have exams here. And the vertical distance here, this is finals. So this is what our picture looks like. And we're predicting, of course, a plane here. It's a regression plane. That's our regression equation. Multiple regression equations, this plane. And in that plane, you can see where those 3 lines were. Well, you can see the tilt. Okay, so where are they? These were exams 90, 80, and 70 here. right there. And you can see the tilt here all has a slight tilt of 0.164. All right, so these are our exams right here, and we have 70, 80, and 90. And now we're going to look at the effect of exams once you control for homework. So we're going to look at this here. All right. And this, you can see that exams have a bigger effect than homework. But again, it controls for, this is the most important point. This is why multiple regression is really cool, because it controls for the effects of the other predictor variables in the equation. If you just look at the simple ones separately, they don't do that. So it gives you more information than just looking at the simple ones. What do I mean by the simple ones? Looking at this simple one right here that has a bigger slope again, and this simple one here. They don't tell you how much of the effect is, when you have correlated x's like this, they don't tell you how much of the effect is due to homework and due to other variables that might be confounded with it. And same with exams. It looks like it has a really big effect. It does. Once we separate out those two effects of multiple regression, it's very nice. You can see how much each contributes. And then you can see what we're going to look at eventually is whether they remain significant. Once you include them in the multiple regression model, some of them that were significant before will drop out because their effects aren't that important once you include the other ones. So we'll look and see if these are both significant. All right. So that's the idea. So let's just do the same thing. Okay, so for those with the same homework, the exam slope describes the effect of exams on finals for those with the same homework scores. So what does this mean? If you have the same homework scores, the predicted final score is what? 0.5824 points higher for each 1 point increase in exam averages. So this is a bigger difference. It's about 0.6 difference predictive value for each exam point. Extra exam point, it means about 0.6 more. Okay. All right, so let's just do this. So let's find these three equations here. Can you see where they're going to be? Here's they're each going to have a slope of what? 0.5824, 0.5824, and 0.5824. But the exams are going to differ. I can draw them in here. Here's the exam of 70, 80, and 90. There's an exam of 100. This will be 90, you can see. This will be 80, and this will be 70. And you can see that exams, the tilt of the plane in this direction is much steeper because exams have more an effect than homework. Okay, so this is 70, 80, and 90. This is the homework right here, and this is the exams. Okay, so let's just get these numbers. This is pretty easy. What are we doing? Now we say for 70. For 70, we're going to put 70 in for homework. So we have 0.164 times 70 plus 11.91. And here we'll put 80 in, right? 80 plus 11.91, and here's 90. So this altogether is 26.679. That's the highest. See, we're only going to, this effect is not going to be so strong. It's just going to be 10 times 0.16, so it'll be about 1.6, about 1.5 difference. So this goes to 25.038, and this is 23.397. Just about 1.5 points difference for a 10-point increase. Okay, so that's the idea. Any questions on that? It's just arithmetic, and the important thing is I want you to get this visual here. Yes.
The endpoint for the exam and finals, like line, it's kind of hard to tell. Right?
It's hard to tell because it goes down, it's cut off at 40. So it's going to go, these lines are going,
I mean, like the top one. Like,
this point?
no, like over the orange line, on the top of the orange line. It's hard to tell where the finals are.
Where the finals are?
Yeah, like
The final, okay, so for any point on here, it doesn't matter, like, for any point, like for this point, you can see it easier. You can see this person aced the final, got like 100 on the final. But you wouldn't guess that from where he lay. He lay what? Look at his homework. You go, here's where he was predicted. I mean, here's where he was predicted in this plane here. But here's where he landed in the homework exam plane. He was what? At a 45 on the homework. And then you go here at an 80 on the exams, but he got 100 on the final. You wouldn't have believed that would have been, that's why he has such a big residual.
outlier.
Yeah, he's an outlier, but he has a big residual, but it was a real, yeah. There's some, so some people did better than in the plane. There's a person that's right on the plane, it looks like. Did just what expected. So the people below the plane have negative residuals. It's hard, some people have a much better visual sense and they can see this very easily in 3D. And some people have to see it in movement or something. Can't really easily look at this and even picture 3D. It's just, some people just have a better sense of that. I hope it helps a little bit to draw these lines in. All right, so now, so here's the equation for the simple one, which I haven't pictured. I didn't picture it here the way I did here. But it's the same idea. You'll notice it's bigger, for one thing, right? It's bigger. This one's bigger. The multiple regression one was smaller. Our multiple regression one, again, is less than this one, the simple one. This is our simple. And why? Why don't we do this one as an eye clicker? Think about why. Why is this multiple regression less than? Why is the exam slope smaller in the multiple regression one? Here's your choices, and let's do this as an eye clicker. It's a lot to read. Is it smaller because there's a negative correlation between exams and homework? So including homework has a negative effect that reduces the exam slope? Is that why it's smaller? Is it because there's a positive correlation between exams and homework, so the effect of homework is combined with exams in the simple regression, so it inflates its slope in the simple regression because it's mixed together? Or is it because there's no correlation between homework and exams? So that makes the slope smaller when both are included. So choose A, B, or C. And let's see what you chose. Great. That's terrific. If we look at this, let's go back to the document camera then. Great. If you look at this, because there's no correlation, remember when there's no correlation, if the correlation between x1 and x2, if they're uncorrelated, then what happens? That means that the slopes are the same. The slopes don't change between multiple and simple regression. If this is equal to 0, if they're uncorrelated, then that means the slopes don't change. They stay the same when you go from the simple to the multiple. So that one's out. This one is the correct one. There's a positive correlation between exams and homework, and between homework and final, and that it's mixing those two things together. So you get the partial slopes. Negative correlation, well, there isn't. And it wouldn't reduce. Okay, so we haven't really talked about what happens when there's a negative correlation. All we've said is, when we've looked at examples where the two predictor variables and the y variable are all positively correlated. They're the easiest to understand. Are all positively correlated with each other. Then the multiple regression, then slopes in the multiple regression will always be smaller. That's the easiest to understand. It's harder to understand where we haven't talked about when there's a negative correlation. When there's a correlation, they're going to change. But how they're going to change is more complicated. But when they're all positively correlated, it's very easy. The idea of partial slopes is very intuitive. So we focused on that. So all the examples I give you will be ones like this, if I ask you what happens to the slopes. But remember, if they're correlated at all, the slopes will change, but they can go up. They don't have to go down. And when you put them in the multiple correlation, they can go up. But that's because some of the variables are negatively correlated. Okay, so now let's go further here. And we're talking about, we talked about interactions before. But you probably, like in this last page, you're probably wondering, how did I know that the three lines would be parallel? In other words, how did I know that the effect that an improved homework score that would make the same difference whether you did well on the exams or poorly on the exams? We really didn't. But that's, how did we know that an improved homework score made just as much difference for students with high exams as for low exams? We didn't. It's just a guess. But that's at the heart of multiple regression. Multiple regression assumes that. Unless you add an interaction term, okay? Which is a multiplicative term. So, multiple regression assumes that each predictor matters just the same amount regardless of what the other predictors have. So it assumes those parallel slopes. But what if it doesn't? For example, it's very possible that doing the homework may make more of a difference in raising final scores for those with low exams than for those with high. If that's the case, then there's an interaction. So I want you to look at this picture here. Okay? And so an interaction, remember, means what? It means that there's different slopes for different groups. So groups have non-parallel slopes. What do I mean by different groups? I mean, I'm looking at different groups. I'm looking at a high exam group and a low exam group. All right? This is all homework predicting final. For each one of these, homework is just what we've been doing. But here, and this is a situation we saw before, where the high exam people also had higher homework, where they were correlated. Homework and exams are correlated. Here they're not. Whether you have, whether you're this group of high exams or low exams, your homework average is the same, right? Same here. But these two, they're correlated. The high exam group, these are the high exams. People with high exams also had higher homeworks. This is the homework axis. And this is the low exams. Okay, these are the two groups. And we said that if you don't include exams, include that group include exams is that you're going to get this overall slope, this picture, that if we're talking about, that has a confounder. If we're talking about causation, it's making homework, this is the overall slope, look bigger than it does once you look at the multiple regression. Then you see it doesn't have as much an effect. There's that strong effect, and here's, it weakens in the multiple regression once you control for exams. So this has correlated x's, and this has correlated x's too. Here, remember what confounding is. Confounding depends on two things. Confounding, there's confounding when you have these two conditions. And the first one is different x's, different x averages. For the two groups. They're correlated. These are correlated x's. And then also that the overall slope, like the orange slope, is not the same as the average of the two group slopes. The average of the two group slopes is just this, and we've got a different overall slope in the simple regression. So that's a very nice. So, when you're talking about causation and you're worried about something being a confounder, you include it as a predictor variable so that the confounding effect is separated out. And these two have non-parallel slopes. So these two have interactions. These two have different x's and a different overall slope. So these two are confounded. And this right here is what I think might be going on. We just haven't looked at it yet. That maybe homework, it's this picture. This is exactly, let's label these. This is plot 1, this is 2, this is 3, and this is 4. And this is right here. This situation is like plot 4. If people who didn't do well on the homework, they have low homework averages, it might be much more helpful for them to do the homework. The higher their homework average might have a stronger effect on their final than people who have high exams. It still helps, but not as big an effect. That might be happening. We have to look at the data to see. So if that was happening, we'd have to include a multiplicative term, homework times exam. All right? That's the idea. Now these two have interactions. Both of these have interactions. Here's the overall slopes, but they don't have confounding. They violate this. Look, they don't have different x averages. And their overall slope's the same as their, okay? So these would be uncorrelated. If homework and exams had nothing to do with each other, which is a rare situation. I mean, that just wouldn't happen very often. All right, let's move on. Are people pretty good? This is just to try to give you a visual picture. This is complicated, and I don't expect it to sink in right away. You're going to see it over and over again. Okay? So if you don't quite get it yet, don't worry about it, please. So now, so for the summary, so if we wanted to add an interaction term, like to look at that effect of homework and exams, we'd have to do this multiplicative term. That would be an interaction effect. Okay? All right, now we're going to have, we're going to look at the assumptions that underlie doing multiple regression. So what assumptions do we have to do multiple regression? Because what do I mean to do multiple regression? To do our significance test, to put error bars on these slopes. So what do we need to do? To use, not just to do it, but to use it to make inferences about a larger population. So it turns out they're exactly the same as for simple linear regression. So I'm not going to spend much time on this because we've seen them, these exact same 4 conditions that we need, 4 assumptions. And the first one is linearity. Okay, we have to be able to, each predictor has to have a linear relationship with the response variable. If you have a curvy linear relationship, you should do something else. Okay, and it also needs to be modeled as a random sample from a larger population, coming from a randomized experiment or coming from, a random sample in order to do any inference. That's just has to be. Okay, and then to use the tests that we usually use, like the confidence intervals based on the normal curve or on the t-curves, the f and the chi-squared, then we have to have what? Independent, which comes from the random sample, equal variance, and with small samples, roughly normally distributed errors. And you'll see this written if you take almost any statistics class. The way they express this is that the errors have to be identically independent and identically distributed, IID, normal, with mean 0 and the same sigma of the errors, the same standard deviation of the errors there. Okay, so these are the same assumptions that we did before. So let's check it with our example. So the 107 students were randomly chosen from a much larger population. We're assuming that. If they're not, we have to check some other things, but let's just assume they were. The plots, they showed a linear trend. And how about the errors? Well, we can only check assumptions about the errors after we do the analysis to see what the errors look like. So we'll check these after we do the significance test. So that's to come. And we're going to be checking assumptions throughout. But honestly, unless you have made up examples, they're always somewhat violated. So what do we do if they're violated? Like already, this one was really violated. We didn't really do it that way. So we need other methods besides this. And that's what we're going to be exploring later on, next week, for example. So random sampling violated. And this happens all the time. So you have to try to assess how closely your sample reflects some general population. For example, if your sample's all college students, you certainly can't make inferences about all adults. There's other ways we can check this too. Linearity violated, this is going to happen a lot. This is going to be after the exam. We're going to do a whole section on this, transformation of variables. So we see that we don't have linear plots, so we're going to look at how we transform our variables to make them more linear, and then how we build confidence intervals around those transformed transformations. The most common one we'll look at is log transformations. We'll do a lot of those after exam 2. Errors not equal in variance. We're violating that homoscedasticity. We need that equal, like if you see a fan-shaped plot, what do we do then? Well, we can do data transformations sometimes. We can do re-randomization methods, and that's what we're going to look at next week, next class actually, or other non-parametric methods, which we're going to look at the end of the semester. The last thing we do. And same for this. If the errors aren't normal, we're going to look at all those again. So what's cool is I'm going to give you just different tools to do the same thing, and we're going to compare them. So when they're violated, even when they're not, lots of times you want to just use other methods and see if you get the same p-values, basically. Okay? So that's what we're going to do. But now, let's just remember the F and the chi-square test. We already saw this analysis of variance. That's what we're going to be doing here. We're going to be using R squared, the F test, and the chi-square test, but this time we have to do it because we have multiple slopes. We can't do Z and T tests on the overall regression effect to see if there's anything in our model. So we're looking at for the overall regression effect, we have to use these F and chi-square tests, and they're going to be exactly the same as what we did before. We just have additional parameters. Okay, so that's what I say here. Now that we have more than one slope, okay, more than one slope, our first test is to test whether any of the slopes in the model are significant. the overall effect, the collective effect of all the slopes together. Is there anything in our model of predicted value? If none of them are, then there's not much point in going on, except special circumstances. But generally there isn't. So we're testing for the overall, this is all for the overall, the collective effect of all the slopes together. So what do I mean by that? I mean our null hypothesis is that all the slopes are zero. There's nothing in our model except for the intercept. It's the same as saying, we're not testing that one because we're just saying all these slopes don't make any difference. And what we're left with is just saying y is equal to the finals is equal to some number. And what would that number be? Well, that would be the average of all the finals. So it's the same thing as saying we have no correlation overall. There's no correlation between anything we predict and what the actual points are, the actual y's are, our predicted finals and our actual finals. It's the same thing as saying that our best model is just using the average, ignoring homework and exams and just saying the average final, maybe in past semesters, is our best predictive. Okay? So now, and the alternative hypothesis is just that's not true, not all, which is the same thing as at least one of the slopes has to be not zero. Not all of them are zero. At least one of them is non-zero. Okay? And so we're just going to do these tests like we did before. And remember, it's just like we've done this before. They just check all significance tests, assume that nothing's going on, the null, and then you get this test statistic. And if it's big enough, if it's far enough, if our sample is so far from where we'd expect it to land under the null, we're going to reject the null. So basically, we're doing the same thing. I'm just reiterating what we always do. The bigger in absolute value, and these are always going to be positive, the bigger the test statistic, and the test statistics we're going to be looking at here are f and chi-squared. That means the farther our observed sample is, how far it randomly landed, we're saying, is from what we'd expect under the null. And that p-value tells how unlikely it is. So the bigger the test statistic, the smaller the p-value. All right. So now, with simple, this is important. With simple regression, we could use, we had the choice. We didn't have to use chi-square. We could use z. We didn't have to use f. We could use t. But now we no longer have that choice. We have to use these y. And again, it's because we can't boil down the difference between what we observe and what we expect into a single signed number like you can with the z and the t. We have, with two or more slopes, we have to look at two or more differences. Some could be positive, others could be negative. So what do we always do in statistics? Instead of taking their absolute value, the average of their absolute values, we don't just sum them up, we square them before summing them up. So these tests are based on comparing sums of squared differences, which are variances, because that's what we have to do when we have multiple groups. And then, of course, this is just like with z and t. If the sample size is large enough, we can use chi-squared, like we can use z, but otherwise we have to use f. Because, so it's the same deal. So as f goes to infinity, f is going to go to the chi-squared, just as n went to infinity, t looks like the z. So with big sample sizes, we can use these two instead of these two. All right, so let's do it now. The rest of the hour is just going to be doing these tests that we've already done before. Okay. So here we are again. I like to use the same example just because we have the visual of it. We've looked at it a lot. And here's our same example. And it has three parameters. Here's B0, B1, and B2. Two slopes, 3 parameters. So our number of parameters is 3. We need that. We need that information, and we need what? We need n, and we need r in 3 parameters. And then we can do a chi-square test and an f-test. Because, remember, let's do the chi-square test first. You probably you remember it as, what is it? R squared over 1 minus r squared times n. That's really easy. So let's do that. Where is, oh, that's what we're going to have to use for r. Let's round it. So we'll say approximately 0.62. It'll be easier. So let's use that for our r. So then we're just going to square that. That's in the numerator. 0.62 squared over 1 minus 0.62 squared. So that's going to be chi-squared times, what's n? 107. So I did that, and I got this chi-square, 66.81. Now, if you remember, when the null is true, chi-squared is about equal to its degrees of freedom. How many degrees of freedom are there? Do you remember the degrees of freedom for the chi-squared? We had it before. It's number of parameters minus 1. The number of groups minus 1. The number of parameters minus 1. Okay? So P is equal, number of parameters is 3, so the degrees of freedom is equal to 3 minus 1, which is equal to 2. So you should remember that when the null is true, we'd expect our test statistic, chi-squared, to be 2. And we got this astronomical one, 66.8. So it landed so far away. This is so unbelievably unlikely to happen by random chance. So we are going to reject the null. But let's just go through it. Okay, so under the null, the chi-square statistic, this statistic follows the chi-square distribution with p minus 1 degrees of freedom. There's a different chi-squared for each number of parameters, for each degrees of freedom. So how do we find the chi-square? We look at a table, like here. All right, here's a chi-square table, and there's just one set of degrees of freedom. Where are we going to be looking? Right here, for degrees of freedom equal 2. All right, and these are the critical values for chi-squared at different p-values. So which one do we want? Let's see. How big a chi-square do we need? Look, this looks huge, but if you want to know for sure how big you need to reject it 5%, to reject it to 1%, if you didn't have a computer and you just want to look at the tables, all right, you have to look at these critical values here. So that's what these are, these critical values. So how big a chi-square do we need to reject the null at 5%? Well, 5%'s right here. So we need 5.99. These are the critical values right here. These are all the critical values. So they're like, you put a star next to them. That means critical values. So we need at least that. Look at ours. Much bigger than that. You need that or bigger. Remember, the bigger your test statistic, the more unlikely it is, the less your p-value. So it's less than 5%. Our next one, how would we know 1%? Well, just look at 1% here. And you have the critical value is 9.21. And at 0.1%, sometimes you'll see it as a decimal. You'll often see it as alpha equals. It's the same thing. Alpha equals, or usually with the p-values, they say it as percents. With alpha, they say it as decimals, but it's the same thing. All right, so this one, 0.1%, which is the same as alpha equals 0.001, and that is even bigger. That's a really big 13.82. So the picture, so before, okay, let's say we, just knowing this, let's do a typical exam question, okay? I'll give it to you as an eye clicker question. Just knowing this, what can you conclude about our p-value? So let's go here and do that. Okay, and I'll start this. So this is r chi-squared. So you're going to compare it to these critical values, and from that, you should be able to decide which one of these is true for our p-value. You can't figure it out exactly, but from the table you know, from these critical values, you know which one of these to choose. So just choose one of those. Okay, just a few more seconds, and we'll see what you chose. Okay, the answer is A. Great. Good job. Okay, so now let's make it a little more explicit here. Let's just draw the picture, and you'll be able to see it more easily. Okay, so now what do you conclude? So let's draw this picture here, just so we can draw these. So we have a chi-square curve with 2 degrees of freedom. So it's very asymmetrical with 2 degrees of freedom. Remember, it's always positive. And we have a curve that looks like, and it never crosses, so it goes on forever. But it keeps getting closer and closer to the x-axis. And here's 0. And what these numbers tell us, right here, these critical values, they tell us the cutoff. So let's do this one. So about, let's say this is, say that, right there is the critical value. I'll put a star here. And that right here is 5.99. That means what? That means from here on in, out is 5% of the area of the curve. So if you have something bigger than 5.99, your p-value is less than 5%. You have less area. Now let's look at the next one. Let's say we go out to 9.21. And that tells you that this area is only 1% of the curve, is beyond there. And the next one is what? 13 point. So the next one is 13.82. And this tells you that from here out is 0.1%. Now, all we're thinking, we're comparing our chi-square statistic. That's what we're doing. So we compare our, what do you always do? You compare our chi-square stat equal to 66.8 to the critical value. And we're comparing it. Ours is off. I mean, I'd have to draw it way over there, but I'll just draw it here because these are drawn to scale. Pretend it was here. It's much, much further. So this is where our chi-square stat is equal to huge, 66.81. So our p-value is almost 0. So this, from here on in, is almost 0%. It's not, but I'd have to give you, it's virtually 0. It's never exactly 0 because it doesn't touch the x-axis, but it's almost 0. So we're going to compare this one, and you compare it to the chi-square, to this, the one that's going to give us the smallest p-value, this one. So we can compare it to chi-squared at 1%. And that's going to be equal to 13.82. And ours, it's so much bigger. The bigger your test statistic, the smaller your p-value. So that means it's to the right here. There's less area. So our p-value, it's so much bigger. So our p-value is so much smaller than 1%. So what does that tell us? If you have a p-value, there's overwhelming evidence to reject the overall null. So we'll reject the null big time. We're almost sure that our model has a signal in it. I mean, our model's that either what? That not all the slopes are 0. It doesn't tell us that they're all significant. So reject null and conclude that at least one of the slopes, maybe both, that at least one of the slopes is significant. One of the slopes is not equal to 0. It could be either exams, probably exams, or homework, it could be, or most likely both, or even both. That's what it means. And later, next time, we're going to then look at the individual slopes and look at how to test the individual slopes using t-tests or z-tests. But for now, we're looking at the collective effect. So we did this chi-squared. Now let's do it by the f. The f's going to give us something very similar. This is such strong data, but let's just remember how to do the f. It's a little harder because there's 2 sets of degrees of freedom, just like the t is harder than the z. So let's just remember how to do it. Okay, so now we're going to do the whole exact same thing, and this time we're using the f-test. Now, the f, they're the same. This is the key part of both. That's in both. And, that's the correlation coefficient. So that's the strength of the predictions, and that's the strength of the errors. And that ratio, the bigger that is, the more evidence you have that your model makes good predictions and that you're going to reject the null. Okay, but the chi-square curves are based on the normal curves, and there's sort of an analogy between the f curves and the t curves. So the f-t test gives you slightly more precision. It's more conservative. The p-value is always slightly larger. You need more evidence to reject the null. But the difference is negligible with large samples. So let's look at this. All right, do you remember how we do this? So here we have r squared, and we adjust the denominator just by an average. Here, the denominator, we're estimating unknown standard deviations, so we have to make that little adjustment. Use SD plus, right? That's what we're doing. N minus p, n minus 1 when we do a mean, n minus 2 when we do a line. Here we're going to do a plane. It's going to be n minus 3, etc. That's what this is about, right? And this, chi-squared, we'll talk about this later, but chi-squared only has, so this makes F tables so complicated. I wish they didn't do this. But anyways, so this is the degrees of freedom in the numerator. And you're going to see that this is completely unnecessary to do, but it's done. You don't have to do that. And then they look so much more alike, but they do it. Okay, so degrees of freedom in numerator, and this right here is the degrees of freedom in the denominator. And of course, when you simplify, you get these 2 different statistics. Okay, so what are we doing here? So we do exactly the same thing we did before. We did the same thing. Oh, we don't have it from previous page. What is our, we're just going to use the same stuff. From previous page, we had R equals 0.62. And then we need to know what else. N equals 107. And we have 3 parameters. This is just from the previous page. Okay, so we're going to do exactly like what we did before. We said for the chi-squared, we said 0.2 squared, r squared over 1 minus r squared. That's this part is the same. All right, over 1 minus 0.2 squared. And then for the chi-squared, we multiplied by n, and we stopped. That was really easy. That's where we are right here. That's really easy. But now we have to tweak this a tiny bit. These little annoying degrees of freedom. Sorry, but they are kind of annoying, especially to teach at this level. But let's just do it. You need to know it. So we have to tweak that by what? By the number of parameters in our model. This measures variance around our model. So this is minus 3. That's because we don't know the standard deviations. We don't know them here either, but we're just assuming we do. We have a big enough sample. All right. Now, so we do that. That doesn't make that big a difference, right? Does that make a big difference? And this, no. But this is what makes a big difference. And that we have to do what? We have to divide by p minus 1. So we're going to divide by what? What's p minus 1? 3 minus 1. So we're going to end up with something that's half as small about, because that's what's going to make the big difference. So instead of getting what we did before, which was 60 something, right? 66, we get 32.4. And that's our f-stat right there. And the degrees of freedom in the numerator, now don't get confused here, I just simplified. The numerator degrees of freedom are here, and that's this. This is p minus 1 right here, so that's 2. And in the denominator, it's n minus p, so that's 104. That's what we've got. Even though when we simplified, it looked like that. All right, so now we're going to find the critical values. So let's find these critical values. Now, because of these two sets of degrees of freedom, these tables are so annoying, you'd have to have a separate table for each p-value. So here it's too, I'd have to give you lots of tables. So I'm just going to give you this one for now. So that is 5%. This whole thing is 5%. So what do? So we go here, the degrees of freedom in the numerator, right here. That's 2. So we're going down here. We're looking at this. And 104. But there is no 104 here, because that would be really long. So the degrees of freedom is 104, and it's between 2. So what people generally do, if it's between 2 lines, they use the smaller line. So we should write that down. So it says, first of all, this is what we're going to get. Now you can see it's very close to that, but it's bigger. So we're going to be a little more conservative here. So we'll say find the critical, okay, from the chart below. So we did. We say f star is equal to 3.15. And I'll just say if degrees of freedom is between 2 lines in the table, use line with smaller degrees of freedom to be conservative. Okay? Because if it's true here, it will definitely, if our f-stat is true bigger than this, then it's definitely going to be bigger than this one. That's what I mean by conservative. Okay, so we've got that. And then we can draw the picture just so you can get the picture again. So here's our picture. And our critical value, and the curve looks very similar. The curve. Remember, when the null is true, f is about 1, not degrees of freedom. But anyway, so we get 3. This is our, here, this is our f star, and it's equal to 3.15. And what does that mean? It means that this whole thing, this is 5%. Now we're going to compare RF, which is way out here. It's actually further, but RF is what? 32.4. That's RF. So our p-value, which is this part, is again almost equal to 0%. Okay? So that's the picture. And so all you're doing is saying you're comparing how the RF stat, so RF stat is equal to 32.4, and we're comparing it to f star, which is equal to only 3.15, and it's so much bigger. So our p-value is so much smaller than 5%. It's close to 0. And of course, we reject the null. Same conclusion. Any questions on that? All right. Yes?
I think you mixed up the Linearity Violated for the f value.
Our F stat is
Up here, 107 minus 3.
107.
Oh, so like that's the denominator, but you wrote down the numerator.
No. Okay, his question is, which is the denominator? The denominator is n minus p.
I know, but like on the process for the F value, you wrote 107 minus 3 on top instead of the bottom.
I know, because when you look where it ends up. Okay, so good question. He's wondering why I wrote this is the denominator, but why did I write it up here? It's because when you simplify this, you're dividing by a fraction, so you're going to multiply by its reciprocal. And when you simplify this, rather than having two fractions, I just wanted one fraction. So when you simplify it, it ends up in the numerator. So don't get confused by that. Good question. Do you see that? Don't get confused by that. It's called the degrees of freedom. It refers to our errors. This is errors around our model. This is what this refers to, variation around our plane. So it's n minus p. That's our errors. This is just refers to how many terms are in our model. It's like this is exactly the same as the degrees of freedom for the chi-squared. Let me explain this, but it ends up in the denominator, even though it's. So don't worry, this is the simplified version. And the reason I let's look at these statistics, and I think you can understand them better. All right, they have different numerators and denominators. Why? First, the denominators. That's what I just explained. So if you look at these denominators here, this is 107. This refers to the degrees of freedom and the errors. And this right here, and the errors are in the denominator. 1 minus r squared is the errors. So this is 104. So that difference is understandable. That's the difference in the variances we see. That's because, why is it different? This explains the difference in the denominators. The difference in the denominators is what? The denominator is 1 minus r squared in both. So this is f, and this is chi-squared. And here, we're dividing by 107, versus here, we're dividing by 104. And it's because it's the same thing. It's a statistic we use. We have to do this SD plus thing. And it's a statistic we use. We make them a little larger. When we have a normal distribution, so we have to assume normality here, but we don't know the standard deviations of each variables and have to estimate it from the sample SDs. So we make them a little larger, and this is what we get. Okay. So you understand that. It's just what we've done before. And that's where that normality assumption comes in, to use the f and the t. Now, but what about the difference in the numerators? Why are they so different? So let's do the same thing. So the numerator here is just r squared. Whereas here we have to divide by 2 if we have 3 parameters. We'll divide by 3 if we have 4 parameters, versus r squared over 2. What is that? And that's what makes the statistic look so different, 32 versus 66. What's that? It's meaningless. No joke. The difference is conceptually meaningless. It's just a historical accident of who decided to name what. So there's these 2 very famous men, Fisher, and that's why F-test, Fisher. He thought it would be nice to divide by the numerator by the degrees of freedom. Why? I think it's great too, because since it makes typical F-stat values about 1 when the null is true, regardless of the number of degrees of freedom. It makes them about 1. Now, what did Pearson do? They're both very hard-headed men. Pearson decided, who discovered the chi-squared, this is Pearson, decided not to divide by the degrees of freedom. So the chi-square stat's typical values when the null is true is the number of its degrees of freedom. That's why there's that difference. So the difference is the real difference is completely analogous to the difference between the z and the t, which have very similar statistics. They're the same with large n. They just happen to look so different because of a historical accident that hasn't been corrected for 100 years. I'm from a philosophy and math background, and that would have been corrected, because math and philosophy have been around for a long time, or physics, we care about unifying ideas. Statistics is a new baby science, pretty much, compared to them, and they haven't gotten it together to make it easy to learn. It would be so much easier for you guys to learn if the terms were all unified and the same. So I'm trying to do a little bit of that. All right, so that's the idea. So let's put little stars by it because it's important. So you'll remember why they have this difference here. It's just, the curves are just shifted. They don't change the p-values. So put a star here and a star here, and that means, no, it's the same thing we're saying here. So when our F statistic is much bigger than 1, or our chi-square is much bigger than its degrees of freedom, we know to reject the null. And how big, how much bigger, that's what the critical values tell you. How much bigger, that's what the critical values tell you. Okay. But this, I'm going to write it down because it's such a useful thing to think about. So if F is much, much bigger, like it was, 66 and 1, you know to reject the null. You know the p-value is tiny. Is much, much less than 5%. But then for the chi-squared, if it's much, much bigger than what? Its degrees of freedom, which is what? P minus 1, then reject the null because the p-value is much less than 5%. So that's a nice way that you can just look at something and get some intuition. And now let's do the end of these problems. Okay, so now we did them by this easy way relating it to r squared, but now what we're going to do is do the table. We're going to do the same thing with the table. So let's just see if we get the same thing, all right? We should get 32.4 again, and we will, but if you want to set it up as a table, which is what's usually done, let me show you how to do that, if you have these 3 statistics. Okay? We already did it real simply, but we could also use this table. Okay? So first of all, what are we going to put in here? SST. It's n, which is 107, times the standard deviation of the y squared. When I did that, I got 11,285.6. So that goes here. Now, how are we going to get these? Remember? Okay, you know that SST, the sum of squares for the model, total, the sum of squares total, this right here, can be broken up into 2 parts. This is SSM plus SSE. And the way that we do it related to r squared, once you know r squared, is this is r squared times SST, and this is 1 minus r squared times SST. So now we know r squared is, because we know was 0.62, and so that's squared. So what we're saying is we're going to break it up into, we're going to break this right here, this into 2 parts. Okay, so that, it's just, so we'll do that. So this is, all I'm doing is saying r squared times SST and 1 minus r squared times SST. So when we did this, what did I get? I got this is 4,338.18, and this is 6,947.42. And that's what goes in here. It's a lot of arithmetic. Once you get this one, look, once you get this one, which is, just do that arithmetic, you can just subtract it from here, and it would give you that one. Because they have to add up. Okay, so once you get that one, just you could subtract it from there. Saves you a little time. Okay. Now, once you have that, the degrees of freedom. Okay, do you remember? They total n minus 1, so that's 106. For the model is p minus 1. 3 parameters. 1, 2, 3. P equals 3. Okay, so that's 2. And this has to be 104. And you know it's n minus p. Okay, so they sum up 2. And now you get these mean squares, right? And remember what you do. You just take the sum of squares here, 4.338.18, and divide it by its degrees of freedom. And I got 2. This is 4,000. You got 2,169. Sorry about all these decimals. This is real data. That's why it's so messy. That's what I got here. And then for this one, sum of squares error. So that's divided by its degrees of freedom, 104. And I got 66.8. And then F is just the ratio of those two. So we should get exactly what we got before. It's a long way to go about doing this once you know R squared. And you'll get exactly the same thing. Okay, one advantage of doing this, though, here you get the standard deviation of the errors. So if you had to get the standard deviation of errors, it's the square root of that. The square root of the mean square error, that's the mean square, is equal to the standard deviation plus of the errors. And so that's going to be equal to the square root of 66.8, which is, I don't know, I didn't do it. 66.8, I don't have a calculator on me, but it will be the square root of that. Okay? It's about 8 something. Approximately 8 something. Is that too small? Does everybody understand that? Just take the square root of this. Here, I'll write it over here. The standard deviation plus of the errors is equal to the square root of 66.8. That's all I'm doing here. I didn't have a space for it. All right, so let's do another example that's much easier. This is hard to read because there's so many decimal places. Let's just do a really simple example, okay? So this is the summary and the practice on the next page. All right, so here's the summary and the practice, and this won't take us long. I know you're kind of tired. But does anybody have any questions? Are you okay? All right. So here, you see this ratio. That's what's important for both. And those are the test statistics, okay? And notice the bigger n is, the bigger your test stat will be. That makes sense. Since the bigger your sample size is, the better able you'll detect a signal in the population. If you had data on the whole population, you could detect any signal. So the bigger your n is, the better you'll see a difference if it exists. Now, so here's 2 practice examples. One is just using R squared, and the other will use the table. Okay, so this first one, it's really easy. So you have some generic model, and you're given this. And we want to compute chi-squared and F, okay? So R squared, 0.1 squared, so that's 0.01. And 1 minus R squared is just going to be 0.99. All right, so compute chi-squared. So chi-squared is going to be 0.01 over 0.99 times n, which is 100. So that's 1.01. right away you know that's not significant because you compare it to its degrees of freedom, and the degrees of freedom is equal to p minus 1, which is what? We have 1, 2, 3, 4. Do you see 4 parameters? So it's 4 minus 1, which is 3. So we'd expect 3, so we know we don't even have to do a significance test. We have to have something greater than 3. So this is going to be a very high p-value. It's going to be greater than 50%. Now how about the f? Let's do the f. So the f is the same thing, and it's 0.01 over 0.99. And instead of 100, what do? We're going to compute its instead of 100, we're going to have what? 100 minus what? 4, which is 96, and 4 minus 1, which is 3. So that's going to be it. And I got is about 1/3 of that, because multiplying by 100 versus 96 isn't much, so it's 1/3 of that. And you compare that to 1, and of course, you don't reject the null. So the degrees of freedom for the 1 is equal to what? P minus 1, which is 3, and the degrees of freedom 2 is equal to n minus p, which is equal to 96. That's what we did there. All right, so that's it. Now the last 2 minutes, I think I can do this example. Really simple example. And then we don't have class on next Thursday. We'll have class on Tuesday. All right, so here's just a practice example. So what are you given here? How many parameters are there? 1, 2, 3, 4, 5. 4 slopes, 5 parameters. So we have p equals 5. N equals, we're going to use that, and that to do the whole problem. All right, so first SST, that's n times STY squared, and n is equal to 35 times 10 squared, so that's 3,500. We'll put that here. We have r squared right here. So r squared is going to break this down into 0.25 times SST and 0.75 times SST. So 1/4 of this is 875, and 0.75 of that is 2625. Degrees of freedom, well, n minus 1, 34, and this is going to be 4 and 30. P minus 1 and n minus p. And then we're just going to say, okay, 875 divided by 4, and I got 218.75, and here I have 2625 divided by 30, which is 87.5. And when you take the ratio of those two, you'll get your F statistic. .5. Okay. And to check that, it's so easy, so much faster to do it this way. You could have just checked it by saying F is equal to 0.25 r squared over 1 minus r squared times what? 30 over 4. Right? Isn't that right? And you can see right away that's 1/3. 10/4, that's 2.5. So it checks out. So the SD plus of the errors is the square root of 87.5, which is 9.35. And we're done. And we'd have to compare this to the critical value. So you'd say compare F equal to 2.5 to F star. And how many degrees of freedom is it? 4 and 30. And we could just look at that, 4 and 30 on the table. 4 and 30. Is that right? No, here's 30 and 4. 4 and 30. 2.69. So what do? So we're going to compare to 2.69. So where's our F, 2.5? Where can we compare it? Right here to 2.69. And it's what? Is it bigger? No, it's less. So our p-value, so p is bigger than 5%. So we don't reject the null, cannot reject null. We might not have anything in that model. All right, that's it. So we finished that, and then we'll finish up on Tuesday this entire section.